Let us next start the 6th chapter on number-theoretic functions. We have already seen a lot about integers, primes, factorizations and whatnot. So in the study of integers and especially their divisors, some functions become really important. Now say a function has the set of positive integers as its domain. So the function is like this, where this is the set of positive integers and this A is some set. Then this type of functions are called number-theoretic functions. Or arithmetic functions. Now we are going to study some arithmetic functions. Although this set actually can have any type of mathematical object, need not even be numbers, but the functions that we will study, which are arithmetic functions, would mostly be integer valued. That is, for them, this would be a subset of the set of integers. To put it simply, we are going to mostly see those arithmetic functions which have their outputs integers. Just that. And the first two arithmetic functions we are going to study are this tau and sigma. So let us next see what they are. So these are the functions tau and sigma. They are defined for positive integer inputs, that is, they are arithmetic functions. And what are their definitions? If you have any positive integer n, tau of n denotes the number of positive divisors of n, and sigma of n denotes the sum of these positive divisors. That's what they are. For example, if your input n is 12, say, now these are the positive divisors of 12, these 6 positive integers 1, 2, 3, 4, 6 and 12. So because there are 6 positive divisors, so tau of 12 is 6 and sigma of 12 is their sum, which equals 28. Now let us next see, there are some other examples also. So these are some values of sigma and tau for the first few positive integer inputs. Tau of 1, for example, is 1 because the only positive divisor of 1 is 1. So there is one positive divisor, that number is 1. Tau of 2 is 2 because 2 is a prime, so it has only two positive divisors, 1 and 2. So the number of positive divisors is 2, that is why this is 2. Similarly, you can see that tau of 3 is also 2 because 3, just like 2, is also a prime, and so it has only two positive divisors, one of them is 1 and the other one is 3. So tau of 3 is also 2. Tau of 4 is 3 because 4 has these 3 positive divisors, 1, 2 and 4. Similarly, tau of 5 is 2 because 5 is a prime, and tau of 6 is 4, and it goes like that. Sigma is the sum of these positive divisors. What happens when you consider sigma of 1? Because 1 is the only positive divisor of 1, so, sigma of 1 is 1. Sigma of 2 is 3 because 2 has the positive divisors 1 and 2, so their sum is 3. Sigma of 3 is 4 because 3 has the only positive divisors 1 and 3. So their sum is 4. So you can see that for prime inputs, sigma value is obtained by adding 1 to it. Sigma of 4 is 7 because 4 has the positive divisors 1, 2 and 4, and their sum is 7. So like that it goes. So from this we have that observation that we can instantly say what the tau and sigma values of a prime are. So let's write that down. So this is the observation that is clearly true, which we have got from these first few values of these two functions. Now next we have a notation that will, it's a notation involving the summation symbol that will simplify many things in our discussion. Let's see what this notation is. Okay, so this is the notation. Actually, we have already used this type of notation elsewhere, but it's new for this subject. So let's see what it means. New for this subject means new for us here. So the symbol is this, it's summation of some f values, f of d, where d is a divisor of n, and by this we will mean the sum of the values f of d as d runs over all positive divisors of n, where n is a positive integer. So this example will make it more clear. F is some function, okay, so we need not really worry too much about f. F is some given function and f of d makes sense. That's all we need. So here say n is 20. What does it mean? It means it is the sum of those f of d where d is a positive divisor of 20. So all positive divisors of 20 have to be considered and those f values are to be added up. So the positive divisors are this 1, 2, 4, 5, 10 and 20. So this sum is what this notation indicates, what it means. Now using this notation we can express our functions sigma and tau. Let's see what that expression is. Because tau of n is the number of positive divisors of n, so it's clear using that notation that tau of n should be this. So that f of d that we have in the general notation in this case is equal to 1 for each d. For each positive integer d of n, f of d is equal to 1. That means we are adding as many ones as there are positive divisors of n. And that will give us the number of positive divisors of n, so that is tau of n. And sigma of n is in fact even easier to understand. It is just simply the sum of all positive divisors of n. So expressed in this notation, tau of 10 for example would be this sum. Oh, I wrote an extra one, sorry. Why though? Why are there? No, okay, the number was actually correct. I confused myself. There are 4 ones here. But why 4 ones? Because 4 is the number of positive divisors of 10. And in fact, the divisors are 1, 2, 5 and 10. So for each one of them, we are getting a 1 in this sum. And that's how we get 4, which is in fact tau of 10. Similarly, if you calculate sigma of 10 with this notation, then you get this sum of the positive divisors, which is 80. Of positive integers. So let us see their structure in terms of prime factorization, and that is given by this next theorem. Say you have a positive integer n which is greater than 1. If n is 1, then of course its only positive divisor is 1, so there is really nothing to say about that. But if n is greater than 1, then from the fundamental theorem of arithmetic, we know that n has a canonical prime factorization. Say this is that factorization, where you understand that these pi's are prime, distinct primes, and these exponents are positive integers. Actually, you can take allow 0 also in the exponent, but in that case that prime power is really not there. So there is no point keeping that here. So we assume that all these ki's are positive integers. Then any positive divisor of n will be of this form, and conversely also. Actually the statement is this: that the positive divisors of n are precisely positive integers of this form, where again those same pi's occur with some exponents this time, and each of these exponents ai, they are non-negative integers. Ai is allowed to be 0. Okay, unlike ki, ai is allowed to be 0, but at the same time each ai is at most ki. It cannot exceed ki for all these i's. Now let us see how we can prove this. This is a fact which is almost trivial, but still it needs a proof. In the first half of this proof, we are going to show that each positive divisor d of n is of that form. Now, among the many possible positive divisors of n, there are two that are always there. One is 1 and the other one is n. And these special positive divisors are obtained for these choices of those exponents. If you choose all the exponents to be equal to 0, then you are getting the number 1 as that d. In other words, 1 is of that form. Similarly, if you make this choice of the ai's, that each ai is say equal to ki, then you get n itself. So the positive divisor n of n is also of that form. So that leaves us with the non-trivial cases. Say we consider a positive divisor d of n next, which is neither 1 nor n. Then n, because d divides n, so n is a multiple of d. Say it is this product, n is d times d prime, where d prime is another integer. Now, because d is greater than 1 and d is also, d not being equal to 1 means d is greater than 1, and at the same time d is also not equal to n. So this d prime also cannot be equal to 1. Why though? You see, if d prime is equal to 1, then d would be equal to n, which is not the case. So d prime is also greater than 1. Now d and d prime are positive integers, both greater than 1. So by the fundamental theorem of arithmetic, each one of them will have a prime factorization. So these are the prime factorizations. So d is a product of some primes, d prime is also a product of some primes, and these primes are not necessarily distinct. Okay, so maybe q1 is equal to q2. We do not have to consider distinctness or non-distinctness here. That's not important here, and that's why we have written where the qi's and tj's are not necessarily distinct. They may be distinct, may not be distinct. We don't have to worry about that. Now let us put these expressions back in this equation and see what we get from. Okay, now substituting those expressions for d and d prime in the equation n equal to d prime, this is what we get. Our original n of course has this prime factorization, and d is this product and d prime is this product. Now you are looking at an equation which tells us that this integer is equal to this integer, and each expression is a product of some primes. That means we are now looking at two prime factorizations of the same integer, which is actually n. So from uniqueness of prime factorization, we know that the primes that are appearing in both the factorizations should ultimately be the same. In particular, each qy that you see here should be equal to some pj. So if you use this information back in the expression for d, that is d originally equals this, now with the information that each qi equals some pj, so you write pj there, and then what you do, you collect like pj's. Maybe say after writing what these qy's are, say you have got p1, p1, p1. then instead of writing it like that, you write p1 cube. So that way you get some powers of these pi's. Note one more thing, that all the pi's may not occur here. However, still we have written all of them. So to account for this or to adjust for this, we will allow some ai's to be equal to 0. That will take care of everything. So in general, the exponents ai's are non-negative integers. They may be positive, they may be 0. However, still something else is needed. We do not simply want ai's to be non-negative integers, but we want them to be less than or equal to ki as well. How can we argue for that? Suppose that there is an index I for which ai is not less than or equal to ki. Say ai is greater than ki for some I. Then what will be the consequence? Let us again go back to that equation. That is, this is our n. This is the factorization of n, the original factorization, in which we have that power which has that exponent ki. It's the power of pi. That is one side, and the other side of course is d times d prime, where d is this expression. And in d also we have that pi, whose exponent is now ai. Now what can you do? Because ai is greater than ki, we can divide both sides by p to the power ki, pi to the power ki. If you do so, the left hand side will be devoid of that pi entirely. Keep in mind that in the original factorization of n, these p's are distinct. They are not the same, okay, no two of them are the same, they are distinct. So once this pi is gone from the left hand side, we do not have it any longer. You can see here, we get, if we are coming from that side, from the left side, as we go rightward, we stop here at this power of the prime pi minus 1. But the very next one, which initially was this, is now not there. Instead, we have the I plus 1th prime. Not exactly I plus 1th prime, but in this order. And then we have the other powers. The right hand side, however, looks like this, where we still have pi to the power ai minus ki. And this is still a positive integral power of pi because ai is greater than ki. So even after cancellation, you still have at least one pi on the right hand side. But is it possible? No, actually this is not possible. Why? Because the right hand side is now divisible by pi, but the left hand side is not divisible by pi. Pi is a prime. If pi has to divide the left hand side, it should be equal to at least one of the primes, but that's not the case. So this is a contradiction, and this contradiction has resulted from this erroneous supposition, which must thus be false. And that is why not just any specific ai, all ai's must be less than or equal to ki. So this is the first half of the proof only, where we have shown that any positive divisor of n must be of this form, where the exponents are like this. But actually this is the complicated half. The other half is very easy and almost. So this is the second half. In the second half, we have an integer of that form, where it's the product of those powers of p and where the exponents are like this. Now what is the aim? The aim is now to prove that d is a positive divisor of n. D is already of course positive, so we now just have to show that d divides n. So we write what n is this product of prime powers. Now you can clearly see that you can write this number as d times d prime. where d prime is this product. If it is a little confusing to see it from this direction, you can just see what the product of these two numbers is. It will just be this. You have to use the rules of exponents. Now the fact here is that d prime is itself an integer in spite of having these minuses. These exponents are all non-negative integers because of these inequalities which are already with us, and that is why this d prime being an integer tells us that d really divides n. So not only should all the positive divisors of n be of that form, which was our first part, these numbers actually are positive divisors of n. So that is the second part. That means the positive divisors of n look precisely like that. That was the entire result. So let me just end the video here itself. Armed with this result, next we are going to see how we can write the functions tau and sigma in terms of prime factorization of the input. So that's what we will see in the next video. So that's just it for tonight. See you tomorrow with a new upload. Until then, this is me, Lucifer from A Mathematical Room. Have a nice day.